It's Paul with a script that shows you some techniques that I think you'll really get enthusiastic about incorporating into your term projects. That's linear regression, logistic regression, and principal components analysis. To start, I'm going to reset the margins for graphics. I should probably have done this much earlier in the course. We like to put labels on the left and the bottom, but we were wasting a lot of space on top and at the right. I've now done away with that problem. So let me start by showing you how to do linear regression with a single predictor. This is the best source of data sets I've found so far. It's the Data and Story Library, DASL, from Carnegie Mellon University. And this looks as though it has lots of wonderful and reasonably sized data sets. It might be a good place for you to look if you're still searching for a data set to use for your term project. The one I found is saved as serial.csv. Carnegie Mellon saves these things as files with tabs in between the entries. So what I did was to load this into Excel and then save it as a comma-separated variable file. But that's about as simple as data cleaning ever gets. So let's load this up and look at it. It's got a large number of breakfast cereals and information like calories per serving, how much fiber, blah, blah, blah. And finally, the Consumer Reports rating. I'm amazed that this rating is given to so many decimal figures, but that's that. And I'm just going to extract the columns for the rating and the columns for grams of sugar. Let's look at those. The correlation is strongly negative. You'd guess that. The more sugar, the less Consumer Reports thinks of you. And if I do a scatter plot, that idea is confirmed. The more sugar, the lower the rating. Let's try to make a linear model of this. Here's the quickest way to get the coefficients of the rejection, of the regression line. The formula, which I prove by straightforward multivariable calculus techniques in the notes, is in the numerator you have the sum of the products of sugar with the mean subtracted off by rating with the mean subtracted off. In the denominator I use just sugar and square it. That gives me the slope of the line, but a quicker way of doing the same calculation is to take the covariance of sugar and rating and divide it by the variance of sugar. In this case, r is dividing by n minus 1, but since it's done in both the numerator and denominator, it doesn't make any difference. It cancels out, and so that's an alternative way of getting the slope. The way you get the intercept is you just take the slope times the mean sugar value subtracted off from the mean rating, and there's our regression line. And it looks pretty good. It goes smack through the middle of the data, and as you know, this has the property that if you take the sum of the squares of the vertical distances from the point to the regression line, it's smaller for this line than for any other. If you want to do this really quickly, of course, this is built into R. You use the function LM for linear model and say, I want rating with linear regression off the sugars column. This is all in the serial data frame, and this produces the coefficients which agree exactly with the ones that we've got. If you ever have to teach a statistics course for people who don't know any linear algebra, this is the way to go. Say, this is a good recipe, cook with it. If you don't like fitting with a straight line, R has a function that allows you to fit the data with a cubic polynomial. And since the cubic polynomial gives a significantly different fit, this is an indication that the linear model is not super good for this. In the companionship script 10M, I showed you how you could fit data with a quadratic polynomial, and in fact you could generalize that technique to work with polynomials of any degree. You could easily write your own function to fit with a cubic polynomial. So, what have we got? We're saying our prediction of the rating is the intercept A plus the slope B times the grams of sugar. And if I plot the predicted rating, I get a bunch of points shown in green here that lie right on the regression line. And the residual is the difference between the actual rating and its prediction. It's sometimes informative to plot the residuals separately, and it would be nice to have two plots. Here's a way of doing that. This says I want two plots vertically, one horizontally. So I redo my original plot. You can see now why I shrank the margins. I've still got enough space on the screen to see something. There's the regression line. And then the next time I call plot, I get something in the space at the bottom. This is a plot of the residuals. They are centered around 0, and if there's something systematically wrong, if the residuals are all positive on one end and negative on the other, your linear model is probably a bad choice. I believe there are courses at Harvard entirely devoted to linear modeling of data, so I'm just scratching the surface of this subject. When you change your graphics parameters, remember to put them back. Otherwise, the next time you do a plot, it's only going to show up in the top half of the window. Now let's split up the variance. Here's the variance of the ratings, 197. If I just use the predicted values, they're not all equal. So this is a random variable with a non-zero variance. It comes out to 113. If I look at the residuals, the variance of the residuals, which is what I was trying to minimize, is 83. And you can check, if you add together the variance of the predictions and the variance of the residuals, you get the variance of the observations. People who do statistics are keen on knowing what fraction of the total variance is explained by the linear model. And this ratio is called R squared. Why? Because it's the square of the correlation R, that I prove in the lecture notes. And so here it is. The variance of the prediction divided by the variance of the observations, which is also just the correlation between the sugar variable and the rating variable squared, is what's called R2. And if you call the summary function on the object that's returned by this LM function, it actually has an entry called R squared that gives you the same number. So if you're playing around with linear modeling for your project, you can use the LM function to get answers in a hurry. But please go back to fundamental mathematics in your final project so that you can use what you've learned in this course mathematically rather than just following canned recipes. Now, I'm going to do this same analysis by working in an inner product space. So here's two vectors that span the subspace, a vector of 1s and the identity function where the y value is equal to the x value. I bind those into a single matrix A that has 2 columns and lots of rows, one for each breakfast cereal. But by multiplying the transpose of A by A, I get a nice symmetric 2 by 2 matrix. I can invert it by using the solve function, and then I can make my projection matrix by matrix multiplication. Let's put that plot up again, and now let's use this projection matrix. Let's take the rating vector and apply the projection matrix to project it onto the subspace, to project it onto the regression line. And let's plot what we got. Sure enough, those points all lie on a straight line, and we can easily find the equation of that line by just not doing the last multiplication by a when we do the projection. That gives us the coefficients, and it gives us exactly what we found before as a and b. Now I can plot the regression line, and I can calculate the residuals. The residuals are found by taking, for each breakfast cereal, the actual rating minus the linear approximation to that rating given by the projection line. And now, since we're working in a vector space, we can say, yes, we did orthogonal projection. Those residuals are a vector which must be perpendicular to the entire subspace spanned by M1 and M2, and if I compute the two dot products, they both come out to 0. And if I take the square root of the sum of the residuals, I discover that I get the minimum possible length of a vector going from the ratings to the subspace that plots up as the regression line. So there are two techniques for linear regression. Now I'm going to show you that the second technique works very well if you want to do regression on more than one predictor variable, so-called multiple linear regression. So let's extract another column from the data frame. Let's get the fat column. If you read consumer reports, you can guess that the rating correlates negatively with the fat content. I assume that if there were consumer reports published in a country where people were starving to death, sugar content and fat content might cause it to correlate positively in that magazine. But in the United States, it's not surprising that the correlation is negative. And there's a small positive correlation between sugar and fat, but they're surprisingly close to orthogonal. Okay, how are we going to minimize the residuals this time? Easy. We make a three-dimensional subspace with a constant vector, sugar, and fat as a basis for that space. Bind it together into a three-dimensional subspace. Multiply the transpose by the matrix to get a square matrix. And R will invert a 3 by 3 matrix as quickly as it inverts a 2 by 2 matrix. There's our projection matrix, and we can make predicted ratings again. If we want the coefficients, remember, just leave out the final multiply in the left when you're computing the projection matrix. So there are our coefficients. The constant, the coefficient for sugar, and the coefficient for fat. And to get the residuals, I now take the rating, subtract off 3 terms, the constant term, the second coefficient times the sugar rating, and the third coefficient times the fat rating. And let's see what we've got. I'm going to first check that these residuals are orthogonal to the constant, orthogonal to sugar, and orthogonal to fat. We really have projected onto this three-dimensional subspace of the space of serial data vectors in such a way that the vector that goes from our initial rating to the closest point in this subspace is orthogonal to that subspace. And what the projection theorem says is that that orthogonal vector has the minimum possible length, that we have actually found a way of minimizing the residuals. If I look at that length, I get 75, and the best I was able to do with sugar alone as a predictor was 79. This is generally true. The more variables you're willing to use as predictors, the smaller the variance of the residuals. And we can split up the variance in the classic manner. There's the total variance of our observations, the variance if you use just the predictions, and the leftover variance of the residuals. As always, the variance of the observations is the sum of predicted variance and residual variance. And if I ask what fraction of our total variance is explained by our linear prediction, that is R2 again. And now we're explaining 62% rather than 57%. You won't be surprised to discover this has all been automated. The syntax is rather interesting. I specify my data frame, I say what I want to predict, tilde, and then with plus signs, I use all the predictors. So if you want, for example, to figure out what happens if you use sugar, fat, protein, and fiber as predictors, a slight modification of this line will do the job. Just to check, here are the coefficients that we got. We agree on sugar, we agree on fat. So our projection matrix technique is replicating the results of the built-in function in R. So that shows you how easy it is using projection techniques to use multiple predictor variables. Suppose we don't want to do a linear model. Suppose we want to try to fit the data with a higher degree polynomial, say one of degree 2. Well, let's load up that file with all sorts of NBA statistics for basketball players. Some players apparently didn't reveal their salaries, so there were a bunch of NA, not available entries in the salary column. It turns out there's a very nice function in R called na.omit, and that will take a data frame and remove all the rows that have NA entries. So here's what we've got. We've got one more cleanup problem. If I look at the salary column has values with dollar signs and commas in them. It took me a while to find this function, but eventually I discovered if you're willing to install the package called readr, remember you only run install.packages once, and then you just load the library when you need it. There's a function called parse_number, and if I apply that to the salary vector, I get salaries as integer numbers of dollars. Now suppose we try predicting the salary with average points per game. Free throws made plus 2 for each 2-pointer plus 3 for each 3-pointer. And if you're a basketball fan, you will say, shouldn't you add in offensive rebounds, defensive rebounds, and assists? Well, maybe you found your term project, huh? But I'm just going to use points per game. In fooling around with the data, I discovered there were some talented but underpaid rookies. So I'm going to throw those out by keeping only the millionaires. I can use the which function applied to the logical variable salary greater than $1 million to get a list of the rows that involve a salary of more than $1 million. And I can use that to extract and save under the same name the salaries for the millionaires. If I do a histogram of this, I see a long tail to the right. There are some really well-paid folks in the NBA. Let's extract the corresponding columns for points per game and do a scatter plot. This is points per game plotted horizontally, salary plotted vertically. And let's try a linear model. We're going to project onto a subspace where one basis vector is a constant vector of the right length, and the second one is points per game. I bind these together into a matrix with 2 columns and lots of rows. I multiply A transpose by A, and I get a 2 by 2 matrix. And to construct the projection matrix, I need to invert that matrix and then use my formula for the regression coefficients. And that's telling us 1 point per game is worth on average another $607,000 in your salary. Let's make the linear function and plot it. It fits the data fairly well, but up here in the multimillionaire category, it does look as though there are significantly more points above the line than below the line. Be interesting to look and see who this guy is. Clearly a real bargain. 25 points per game on the average for a paltry $5 million a year. Well, all we have to do is add the square of the number of points per game as an extra predictor, and then we do exactly the same thing again. Make a 3 by number of players matrix, turn it into a square matrix, invert it, find the coefficients of the regression model, and now we have a quadratic function that models the data. And when I plot that, I see that it gives a slightly better fit. Frankly, I'm surprised that there's not a larger coefficient on the squared term here. I assumed that salaries were a strongly nonlinear function of performance, but if you use only points per game, that doesn't seem to be the same. Now let's move on to logistic regression. Suppose someone tells you the Red Sox scored 6 runs in yesterday's game, and they tell you nothing else. Well, you say 6 runs, more likely than not, they won that game. But an interesting question is, as a function of the number of runs scored, what is the probability of winning a baseball game? Well, let's load some data. We have data from the 2013 season, and that includes information about whether the game was won or lost and the number of runs the Red Sox scored. To do logistic regression, I need to convert this won-lost problem into a Bernoulli random variable. Okay, Sox won-loss double equals the string W. That's either true or false. Most of the time, R will treat that true as a 1 if it makes sense to do so, but I don't want to take any chances. So I'm going to use the as.numeric function to convert it to a 1, and now you can see the vector that I call wins has 1s and 0s in it. 1 for a win, 0 for a loss. Let's extract the runs scored, and let's do a scatter plot. Okay, this scatter plot is correct. This is saying there are a bunch of instances where the Sox scored a certain number of runs and lost the game. There are other instances where they scored a certain number of runs and won the game. And you'll notice you can never win a baseball game by scoring 0 runs. Let's use the quickest way of getting the slope of the projection line, the covariance over the variance, and the quickest way of getting the intercept, and attached to this plot our regression line. This is just stupid, isn't it? It says my prediction is that if the Red Sox are shut out, they have about a 20% chance of having won the game, and if they scored 16 runs, the probability that they won the game is about 130%. That's the problem with linear regression for this type of data, and the problem is solved by doing logistic regression. So this is one case where I can't show you an example where in a simple case I can do all the mathematics by hand. In this case, we have a problem that can only be solved numerically. What I've got here is a function derived in the notes that computes minus the log of the probability that if I use parameters alpha and beta for my linear regression, logistic regression estimate of the probability, a function that always has a value between 0 and 1, this is the logarithm of the probability that I would generate all the observations. And the general strategy here is known as maximum likelihood estimation. What you try to do is find values of the parameters that maximize the probability for generating the existing data. For 20 years I worked in speech recognition, which is all based on maximum likelihood estimation. Well, R will do this for us. You may or may not have to install this package, but in any event, you have to load the library stats4 to get this MLE, maximum likelihood estimation function. And what you do is give it the function, and you have to give it a starting point. Remember, with Newton's method, you frequently had to have a reasonably good estimate before you could find the exact solution that you wanted. Here, I discovered giving it an estimate where alpha and beta is equal to 0 was good enough to get results. And from the results, I asked for the coefficients, and it gives me the values of alpha and beta for my logistic regression function. So I now have to plug those into the function. This coef1 goes for alpha, this coef2 goes for beta, and I can then plot the function. It's shown in blue, and this has the properties we want. This function has a value that can't be less than 0, it can't be greater than 1, and it actually does a very nice job of predicting the probability of winning as a function of the number of runs scored. Let's try it out. 50% chance of winning. It looks as though that's somewhere in between 3 and 4 runs. So I use the which function to find a vector of indices for all the games where the Sox scored 3 runs, and I take the mean number of wins for those games and discover that when you score 3 runs, you win 34% of your games. If, on the other hand, you score 4 runs, you win 63% of your games. And so this has correctly found the breakpoint between less than 50% wins and more than 50% wins. And you notice it is showing a much greater increase for that 4th run than the rather silly linear model did. What about games with 7 runs? Well, for games with 7 runs, the linear model is predicting around 75 to 80% wins. Actually, when the Sox scored 7 runs in that season, they won 88% of the games, and that's predicted quite nicely by the logistic regression model. If you ask for 9 runs, both models say close to 100% wins, and indeed, when the Sox scored 9 runs or more, they won 100% of their games. So anytime you have a data set where there is some variable that's either 0 or 1, and you want to predict it on the basis of various other columns in your data frame, logistic regression is the way to go. I've never tried doing this with more than one predictor variable. That might make a good project too. Final topic, principal components. This is actually based on some analysis that's done in conjunction with another of these data sets from the DAZZLE database at Carnegie Mellon. This is a file menstrack.csv, and if you look at it, you'll see what it's got. For a large number of running events, everything from the 100-meter up through the marathon, it has the best time ever recorded for 50-some countries, and this data is a couple of decades out of date, as you will become aware when you see that among the most successful countries are East Germany and the USSR. Let's extract just 4 of the columns. I'm extracting the 100 meters, the 400 meters, the 1500 meters, and the 10K run. I make the covariance matrix from that, and needless to say, as a covariance matrix, it's going to be square. You say, why is the variance for the data for the 1500 meters so small? The answer is those times are measured in minutes rather than seconds. But it turns out that doesn't matter when we're doing this principal components analysis. Okay, I'm going to do this exactly as it's described in Hubbard. There are other ways of doing this that lead to the same result, but I want to be consistent with the textbook. For doing principal components, you have to center your data. For what we were doing with projection matrices, you don't have to center your data, but in this case, the centering is essential. So I will do it Hubbard style, and after about an hour of snooping on the internet, I found an R function that does this in one step. The function is called scale. If I set center equal to true, what it does is it subtracts off the mean from each column. And one of the options is I can set scale equal to a vector with one entry per column. What the Hubbards want us to do is to divide by the square root of the number of entries. I'm actually going to divide by the square root of 1 less than the number of entries, because that will give me exact agreement with what R calculates for variances and covariances. So this is what the Hubbards call phi of a random variable. First, you center it by subtracting the mean, then you rescale by multiplying by the square root of the probability for each entry. Let's check that we've got this right. The mean is indeed 0, and the sum of the squares is equal exactly to the variances. It's exactly equal because I chose to divide by the square root of m minus 1. Okay, this matrix is far from square, but we know how to deal with that. We multiply A transpose by A, and we've got a nice symmetric matrix, a matrix to which the spectral theorem applies, a matrix that has real positive eigenvalues and orthogonal eigenvectors. In general, a square matrix doesn't necessarily have all positive eigenvalues, but the matrix you make by multiplying A transpose by A can easily be shown to give no negative values. So all its eigenvalues are going to be positive. What are they? Well, I call the eigenfunction and look at the eigenvalues. And here I find something quite interesting. The first eigenvalue is much, much larger than the others, and the smallest eigenvalue is really tiny. This is an indication that principal components analysis is going to be really helpful, because what this means is there's some linear combination of these 4 columns that accounts for most of the differences between the countries. Let's find the corresponding eigenvectors. This is not P, a projection matrix. This is P, a change of basis matrix, the context in which you first met a matrix called P. It's got an inverse that's easily computed, and as you will recall from the first term in Math 23a. P inverse times this matrix times P is a diagonal matrix whose entries are the eigenvalues. Now we've got a change of basis matrix, so we can take these centered data for the best times at the 4 running events and express each row relative to the new basis of eigenvectors. Unfortunately, I have to multiply by the change of basis matrix on the right rather than on the left. That's because the natural thing to do was to use the data as columns rather than as rows. So let's make a new data frame now and see if we can figure out the meaning of some of these eigenvectors. So I make a data frame where the first column of the data frame is the country name, and the second column is the value v1, which is the first column of the eigenvector matrix. That is, this is the component, the coefficient of the first eigenvector for each country. Let's see what that data frame looks like. We've got a bunch of countries, and along with it, we've got the coefficient of the first eigenvector, v1. Here's a clever way of sorting a data frame. What you do is to say you want to take as your row value the order based on the v1 component. There's a way of doing this either ascending or descending, but I've forgotten how to do it. Let's look at what we've got here. Okay, down at the bottom, we have USA, USSR, West and East Germany, Kenya, the UK, Australia, Italy. These are countries that typically win a lot of Olympic medals. What have we got at the top? Cook Islands, Western Samoa. These are not countries whose athletes frequently appear on the podium to have their national anthem played. So it looks as though what we found with this first principal component is a vector that represents overall Olympic success. Now, before we go to the next one, I want to go back and look at the original database here. Show you something interesting. Look at the 100-meter column. Bermuda. I've never thought of Bermuda as a source of great Olympic athletes, but the best time in the 100 meters is surprisingly good for Bermuda. Having noted that, let's go back and look at the second eigenvalue. So now I'm making a data frame where for each country I include the coefficient of the first eigenvector and the coefficient of the second eigenvector, and I'll order this on the second eigenvector now. And let's look at the top. Well, you say, this includes some countries that do very well, and it includes other countries that do terribly overall in the world of international track. But right near the top is Bermuda, and we already noticed that Bermuda had an anomalously good best time in the 100 meters. And I think that the interpretation of this second eigenvector is that it measures to some extent whether a country excels at sprinting or excels at distance running. When you're doing principal components analysis, the frustrating part is trying to figure out what these principal components mean, and we've managed to give a good interpretation on the first one, and a fairly good interpretation on the second one. Well, let's make a new data frame where we keep the components on all 4 eigenvectors. Now we've done a change of basis, and a change of basis is invertible. We should be able to reconstruct our original data from this database, and I want to confirm that that's possible before doing anything else. So I can use the matrix P inverse to do a reconstruction of A and confirm that I did get back precisely the centered scaled variables that I started with. In order to get back the original raw data, I have to undo the scaling, and in order to do that, I divide by 1 over that square root that I originally divided by. But this is still centered data. I have to go back to my original matrix and subtract off negative column means, that is, to add back in the column means that I took out to center the data. And when I do that, you can see I have reconstructed the data perfectly. Now let's see what happens if we try to do the reconstruction, replacing the component along the 4th eigenvector by 0. This is data compression. If I do exactly the same thing, I know that it works perfectly if I use all 4 eigenvectors. I undo the scaling, I undo the centering, and compare, and you can see I've got a remarkably good reconstruction. With one of the 4 components missing, I'm still saying best time for the 15K is 29.35 rather than 29.36. So I'm getting remarkably good accuracy by ignoring that 4th eigenvector. And the reason I knew that that was going to work is that the corresponding eigenvalue was close to 0, meaning that this vector wasn't important in accounting for the differences between countries. Well, let's see what happens if we try using just the 2 eigenvectors that we have interpreted. So we're using 2 principal components now. All I do is replace the coefficients of the 3rd and 4th eigenvectors by 0, carry out the same reconstruction procedure. This isn't great, but it's still pretty good. So what this is saying is from the times in these 4 events, I can construct a pair of linear combinations that allow us to do a pretty good job of reconstructing all the data. And if you read the discussion of eigenfaces in the textbook, you will see that that's exactly what Facebook does with faces in order to set up a face recognition algorithm. This is the basic idea of compressing your data by principal components analysis. Well, I've gone on for an awful long time, but this is actually going to be the last of these database scripts, because you're now ready to get going on your project, and I hope that with this last one you found a bunch of tools that you will be tempted to apply.